Hi, Rich Neapolitan. We talked about Bayesian networks and influence diagrams, and they were always just created. I said one way to create them is based upon the knowledge of an expert. We simply use the causal relationships that the expert believes are present amongst the variables. But they can be learned from data also. All right. The techniques for learning from data initiated in the early 90s with some researchers at Carnegie Mellon, largely, Spiritus, Gleamore, and others. And Uta Pearl at UCLA had a lot to do with it. In fact, he won the Turing Award just a couple of years ago for his efforts in this domain. I'm going to be talking about learning Bayesian networks from data, but I'm going to center it around the idea of learning causality because it gives you a much more intuitive feel for learning it. So I'm going to talk about learning causality by modeling causality with Bayesian networks. This lecture today is just going to be about causality. And then the final lecture, the one next time, will be about how we learn them. All right, so today I'm just going to be talking about causality. Learning Bayesian networks from data consists of learning the structure of a DAG from the data. All right, suppose we have data concerning smoking, lung cancer, bronchitis, feed, and chest results on many patients. So all we've got is a table with the patients as the rows and the values of those variables as the columns. We want to learn the structure of a DAG in a Bayesian network representing them. We might learn this DAG, all right? So that is our goal, all right? From a table or a data file on a bunch of variables, we want to learn their structure, how they are related structurally in a Bayesian or causal network. Rather than asking the expert, the other way that we talked about before is we told the expert we have these 5 variables, you identify their causal relationships. There's 2 approaches to learning structure. The score-based approach, we assign a score to the DAG based on the data. This approach is discussed in the text Contemporary Artificial Intelligence. It's not nearly as intuitive as the other approach, which is the constraint-based approach. And that's the approach largely forwarded by Uta Pearl, who I mentioned before, and the researchers at Carnegie Mellon. And in this approach, we learn the DAG from the conditional dependencies that the data suggests are present. I should mention that in my own research experience, I have found more use for this approach, but this particular approach is more intuitive. So it's better, I like discussing this approach. I'm not saying that this approach isn't more useful, just my own particular research has done better using this approach. I'll discuss the constraint-based approach. Ordinarily, like I said before, the Bayesian networks represent causal influences, so I will frame the discussion in terms of causation. The material is based on my online tutorial which I gave at the KDD conference about 5 or 6 years ago, and you can view it at this website. All right, it's similar to these voiceover PowerPoints, except you actually see me lecturing, and it's longer than what I'm going to be giving you. Okay, I mentioned it again. All right, let's just go with that. Today's talk, I will only introduce the notion of causality within the context of Bayesian networks. So I'm not going to talk about learning them. I'm going to introduce the notion. The notion, as I mentioned before, is forwarded in these books. Pearl originally talked about in '88. I talked about it at the same time in '89. As I mentioned earlier in previous talks, we met at this Uncertainty in Artificial Intelligence workshop in the '80s, and these ideas grew out of that. Here's Spiritus. Those are the researchers at Carnegie Mellon. They wrote a book in '93, another one in 2000. Pearl wrote yet another book in 2000, and I wrote one in 2004 myself, once again. So it concerns variables influencing other variables. The smoking caused lung cancer. It does not concern what we call token causality, which is a one-time causal event. Did the gopher running into my golf ball cause it to go into the hole? See, in this case, there are variables where we have a bunch of patients who smoke, and some have lung cancer. We want to determine in a probabilistic way the causal influence of smoking on lung cancer. This is a one-time event. We can't repeat over and over again the gopher running into my golf ball, so I'm not going to be talking about this kind of causality. Here's a common way to learn the type of causation I'm talking about. It's via a manipulation experiment or a randomly controlled experiment, and we can represent such an experiment with the Bayesian network. There's a manipulation variable where the probability manipulated is 0.5. We put half of the subjects into the manipulated group, the other half into the non-manipulated group. All those people in the first group we make smoke, so the probability of smoking given you in the manipulated group is 1. All those people in the other group we make not smoke. And then we measure to the extent that they have lung cancer. To the extent that the people in this group have lung cancer and this group does not, tells us how much it is smoking causes lung cancer. You realize the difference between manipulation experiments and observational experiments. If we just observe a correlation between smoking and lung cancer, it may not be that's because smoking causes lung cancer. Maybe lung cancer causes smoking, but when we do the manipulation, the direction of the arrows are in this direction. And if the people manipulated to smoke have lung cancer more than the people manipulated not to smoke, that can tell us smoking causes lung cancer. We do not really want to manipulate people and make them smoke. There's certain ethical considerations about that. Can we learn something about causal influences from passive data without doing manipulations? And that's what this area of research is all about. As I just mentioned, if I just look at passive data and smoking, and I find smoking and lung cancer correlated, it could be that's because smoking causes lung cancer, as we suspect. But there are other explanations. The correlation could mean that lung cancer causes smoking. And again, because we know these variables, it doesn't seem very reasonable that having lung cancer would make somebody suddenly crave nicotine. But if this shows us X and Y, this correlation would not really say that this arrow went in any particular direction. And that's what we're talking about learning from passive data. We're talking about if we don't even know what these are, we don't use our prior knowledge of the variables, how can we distinguish the direction of this arrow? And those aren't even the only explanation. It could be they have a hidden common cause. The tobacco industry actually argued this at one time, that the genetic defect causes people to smoke, which also gives rise to lung cancer. Again, I talked about this before. If two variables have a hidden common cause, then knowing the value of this one makes this more likely to have some particular value, which makes it more likely you would also have lung cancer, and you would observe this correlation. It's difficult to learn causal influences when we have data on only two variables. And that's the problem that researchers faced until 1990, when this research was done, is that we wanted to infer causation from correlation, but we couldn't really because we only had data on two variables. We'll show that we can learn causal influences if we have data on four variables. Oddly enough, unless you make some assumptions about time order, you need four variables to actually learn a causal event based upon reasonable assumptions. All right, let's talk about what a causal graph is. A causal graph is a directed graph containing a set of causally related random variables such that there's an edge from x to y if and only if x is a direct cause of y. What do we mean by a direct cause? Here's a study done in rats by Lug et al. In 1995. They didn't draw this diagram, I drew it based on the study. Testosterone has an effect on dihydrotestosterone levels, which in turn has an effect on erectile function. Now in their study, they found that they shut off people's natural production of testosterone, and they fixed their DHT levels. All right, if they fixed them to high and then manipulated testosterone levels, the erectile function was normal or good. So once they fixed the DHT levels, testosterone level had no effect on erectile function. They fixed DHT to low, erectile function was poor, and the testosterone levels had no effect on that. They did not fix DHT levels. If they raised testosterone levels, they found an improvement in erectile function. So this study indicated that this is the causal graph, that testosterone has a causal effect on DHT, which in turn has a causal effect on erectile function. And so testosterone is not a direct cause of erectile function. And in a causal graph, we would not draw the edge from T to E. This is the way we would draw it. So that's what we mean by a causal graph, that there's only an edge between direct causes. Now, whether a variable is a direct cause or of another depends upon the particular variables in the model. If DHT wasn't in this model, then testosterone, if this variable wasn't here, in that model, without DHT, testosterone is a direct cause of erectile function. So again, it depends on what variables in the model, whether a variable is a direct cause or not. Here's the causal Markov assumption. If we assume the probability distribution of a set of observed variables satisfies the Markov condition, the causal DAG, we say we're making the causal Markov assumption. Again, we know what the Markov assumption is. It's the same assumption we said before about a probability distribution of the DAG. If we assume that this is true for the causal variables we are observing, we say we are making the causal Markov assumption. Here is what we already know. Probably, I'm repeating it here. It's what we covered in previous talks. Probability distribution satisfies the Markov assumption if each variable is independent of its non-descendants conditional on its parents. That's what we've covered before. Example. In these examples, I'll use a capital letter to denote both a binary variable and a value of the variable. Here's a classic example that I use. A cold can cause sneezing and runny nose. So sneezing and runny nose are not independent. The probability of sneezing, given that you have a runny nose, is greater than the probability of sneezing. Why? Because sneezing makes its cause, a cold, more likely, which makes it more likely the other effect of a cold, a runny nose, is present. So it's not true that sneezing and runny noses are independent. However, once we know the person has a cold, they have a fixed probability of sneezing and a fixed probability of runny nose. So the probability of sneezing given a runny nose and a cold is the probability of sneezing given a cold. I've alluded to this somewhat before in previous talks, but I'm making more explicit in this notion of causality. That is, independent, sneezing and runny noses are independent given a cold. Once I condition on the common cause of these two effects, they are rendered independent. And that's the causal Markov assumption. It appears to hold based on this intuitive argument, so that's why researchers assume it holds. Here's the reverse example. This is actually made up by Uta Pearl, that burglars and earthquakes are independent. We're talking about earthquakes like 2s or 3s on the Richter scale, not major 7s that would cause burglars to loot. So a burglar does not make a small earthquake any more likely, and an earthquake does not make it likely that a burglar would show up. Pearl noted that both these conditions can make his burglar alarm go off. Tremors make his burglar alarm goes off, and of course a burglar should. So these two variables have a causal effect on alarm. As I mentioned before, these two variables are independent. But this is the reverse side. It's not the causal Markov assumption, but it shows you how causal variables are related. And I'm mentioning it now. Once I condition on the earthquake, these variables are no longer independent. They are rendered dependent. All right? Because once I know the alarm went off, there's a probability of a burglar being present. What happens as far as once I know the alarm went off, there's a probability of an earthquake, all right, and of the burglar being present, all right. But now I find out later, so my alarm went off and I figured that there's a decent chance I've been burglarized. But then I later find out, I hear on the radio that there was a slight tremor or an earthquake. The story goes that I wasn't at home, the alarm went off in my office. Well, now the earthquake explains away the alarm, all right, making it less likely you've been burglarized. So probably a burglar, given the earthquake and the alarm, is less than the probably burglar given an alarm. Psychologists call this discounting. That once you know a common effect, finding out one cause is present makes the other cause less likely. Knowing this effect doesn't create a causal relationship between these variables. That's silly. It creates a probabilistic relationship. In other words, of all the times your alarm goes off, when there's also an earthquake, a smaller fraction of those times have been burglarized when there is no earthquake. So burglars and earthquakes are not independent given alarm. E discounts B. All right, here is our example with lung cancer, etc. I've talked about this a little bit before, but let's look at it again. Lung cancer makes bronchitis more probable. That's what I'm saying. A probability of bronchitis given lung cancer is greater than the probability of bronchitis because lung cancer makes a history of smoking more probable, which makes bronchitis more probable. But once we know that the person smokes, they have a fixed probability of bronchitis and a fixed probability of lung cancer. So once you know the person smokes, lung cancer has no effect on the probability of bronchitis, which is the causal Markov assumption. The probability of bronchitis, I mentioned this before, and this surprises some people when they first see it, goes up if there's positive chest x-ray. Because the chest x-ray makes lung cancer more probable, which makes smoking more probable, which makes bronchitis more probable. But once I know this person smokes, they have a fixed probability of bronchitis. The chest x-ray cannot make it can still make lung cancer, it still makes lung cancer more probable, but this can't affect this variable, so it can't in turn affect this one. So once you know the person smokes, bronchitis is independent of positive chest x-ray. Independent bronchitis of both lung cancer, both of these variables. Once I know this variable is present, bronchitis is independent of both of its non-descendants, which is lung cancer and chest x-ray results. What are the exceptions to the causal Markov assumption? I mean, everything in statistics involves assumptions, and we have to know what these assumptions are and know that there's exceptions. The first one is hidden common causes. If there's another cause of smoking and runny nose, these two variables would not be independent. Conditional on a cold. This is actually the assumption which is probably violated the most, and it's hard to argue that it couldn't always be present. In this case, hay fever can cause these two. So these three variables really probably don't satisfy it because of this hidden common cause. Now it turns out we can still learn causation even when there are hidden common causes, and I'll show you that in the next talk. But it calls for a little bit more work, but again, in this case, sneezing and runny noses are not independent given cold because if there is a hidden common cause. Causal feedback. Bayesian networks in general assume a direction, all right, and there's some variables that have feedback. Classic example is studying. If you study hard, you're more likely to get good grades, and good grades will encourage you to study harder. Selection bias. This is an interesting example which, again, people don't realize until you usually if you bring their attention. Let's say finasteride. Finasteride is a medication marketed for hair loss. And it causes hypertension. I mean, it doesn't really, but I'm making it up for this example. And it doesn't that I know of. And let's say hair loss also causes hypertension. Maybe you're upset that you're losing your hair, so your blood pressure goes up. Again, I'm making this up. I don't know that this happens. But let's say this is true. And let's say finasteride and hair loss have no causal effect between each other. Let's say we obtain data on only these two variables, and we happen to do a convenience study where we happen to be in a hospital or in some kind of sample where everybody has hypertension. So we take a sample of people who are suffering from hypertension. When we do that, that's often called a convenience sample because it was convenient for us to get such a thing. Well, this is called selection bias. I selected a group of people who have this condition, And that creates a probabilistic relationship between the finasteride discounts the hair loss. So when you take finasteride, all right, it makes it less probable that you have hair loss because finasteride explains away the hypertension. So the finasteride would appear to have an effect on hair loss in this convenience sample when it really does not. That's called selection bias. Now, I made up this example. Merck is the company that markets finasteride for hair loss, and they did not do a convenience sample. They did a very large-scale sample, and I think it's 6,000 people or so, and they did find that finasteride does, in fact, reduce hair loss. So this is simply for the sake of illustration. All right, as I notice here, these two are not independent in our observed distribution. All right, the entities, this is going out on a limb, but it's something that philosophers talk about more. The entities in the population can't, if they're units of time, it can cause, usually our entities are what? Individuals in medicine, right? What if we were looking at time units as being the records? The year 1990, year 1991, year 1992, and we took the variable, which is the Dow Jones average, and my hairline. In the causal graph, these are probably unrelated, all right, because there's no reason the Dow Jones average should have an effect on my hairline. But if I observed these variables in time, there's a correlation here, at least through the 80s and the 90s. As the Dow Jones average went up, so did my hairline. So you definitely see a correlation between these two. But there's no causal relationship. So two variables that happen to increase or decrease in time will appear to be correlated when there's no causal relationship among them. Evidence of this is when the stock market went down after 2000, my hairline did not start going back down. So that kind of indicated that this causal relationship did not really exist. Perhaps the condition that is most violated is that there can be no hidden common causes. And I'm going to come back to that later. Now I want to proceed with this example to show you another example. We talked about this before, finasteride, DHT, and erectile dysfunction. There is a conditional independency. Actually, I didn't talk about this example. I'm sorry. I had testosterone here, DHT, and erectile function, and they studied by Lug. Here is a causal graph concerning finasteride, DHT, and erectile dysfunction. Finasteride is the medicine marketed by Merck for hair loss. It does this by lowering DHT levels. So there is this causal relationship, and there is this causal relationship between DHT and hair loss, which I haven't shown in this model because we're not concerned with that right now. That lower DHT will make you grow more hair. But it also has a causal effect on erectile dysfunction, is the study by Lug et al. Showed. So this is a causal graph. But yet in Merck's study, finasteride did not have a causal effect on erectile dysfunction. So there's a conditional independency in this graph that is not entailed by the Markov condition. That is that finasteride and erectile dysfunction are independent, and that's what the Merck study showed, independent E and F. Now, why is this true? Well, one explanation that I developed, and I'm not sure if Merck says this, finasteride will lower your DHT to a certain minimal level, which is enough to help with hair loss, but you still have enough to have erectile function. So there's some threshold value of DHT that a mammal needs for erectile function, and finasteride will not lower it below that threshold level. All right, regardless of whether that's true or not, the Merck studies did indicate that these two are independent. We already know these are dependent and these are dependent from other studies. So this is a conditional dependency that is not entailed by the Markov condition. The causal faithfulness assumption says we assume the Markov condition, the observed probability distribution of a set of observed random variables, satisfies the Markov condition with the causal diag. And we assume all the conditional independencies in the observed distribution are entailed by the Markov condition. In other words, we assume by looking at the DAG, we can read off every conditional independency that exists in P. It's called a perfect map. The P is a perfect, or the graph is a perfect map of P. And when that's the case, we say we're making the causal faithfulness assumption, that the DAG is faithful to the probability distribution. What are the exceptions to the causal faithfulness assumption? Well, it's all the exceptions to the causal Markov assumptions, the four I showed you, plus you can't assume unusual causal relationships, as in the finasteride example. They can't be present. That's strange. It's unusual when A has a cause on B, B has a cause on C, but A does not cause C, but it can happen. So that can't be going on. And then we have causal faithfulness. All right, next time I will be talking about, if we make the causal faithfulness assumption, how we can learn causes from data. Here are some references for this material. All right, those are all references which you can view this video and stop it at this point to see the references, or you can ask me for these references. I can send them to you. They're actually all in the textbook, Contemporary Artificial Intelligence.